Hi everybody, welcome to my talk. Today I will introduce to you Hornero, our work on thunderstorms characterization using visual analytics. Thunderstorms are among the most prominent high-impact weather events. They produce natural disasters such as extensive flooding, dangerous hail masses, and strong winds. During a thunderstorm outbreak, expert forecasters need to analyze in detail large amount of data, and frequently they have to work in a very short time to provide timely alerts. These big data may come from observation systems such as satellites, weather radars, weather stations, and the data sources provide with new information in the order of seconds to minutes. On top of that, relevant events may take place simultaneously at different locations over the same region of interest. Therefore, analyzing thunderstorms is a critical task in operational weather forecasting to avoid economic loss, to prevent disasters, and save lives. That is why operational forecasters need efficient tools to surveil, to quickly detect, prioritize, and issue warnings about potential weather hazards in a matter of minutes interactively on a daily basis. We have been working for several years in close collaborations with meteorologists and researchers from the National Weather Services and the Center of Research of the Sea and the Atmosphere in Argentina. Together, we found a gap between existing current weather forecasting and storm tracking systems and our forecaster needs. Although they have powerful tools for data analytics, they are lacking different levels of abstractions and topological visual features that can accelerate the analysis of thunderstorms and help forecasters in efficient decision making. That is true in particular in very short-term weather forecasting, where they have many tools to visualize weather radar data and trajectories, but they need software that can integrate storm tracking results, radar data, and storm properties at different levels of abstraction. And all of that with enough simplicity to allow them making decisions in the context of very short-term weather forecasting, namely nowcasting. To fill this gap, we developed a visual analytics tool centered on our forecasters' task workflow. Their task workflow is based on the task workflow recommended by the Warning Decision Training Division of the National Weather Service in the United States, and it is adapted to the National Weather Services in Argentina. We identified key tasks that expert forecasters perform daily when facing a potential severe weather event associated with thunderstorms. The first task is surveillance of storms in operating weather radars. Then, the forecasters do a ranking of high-impact storms. Afterwards, further analysis of the storm structures and associated phenomena. And finally, the forecasting, the decision-making, and issue warnings of severe weather events. That's a key task. For that, we propose Hornero, our visual analytics solution for thunderstorms characterization. Our solution supports experts in these tasks: surveillance, ranking, further analysis, and forecast of severe weather events. We do that by means of visual features to overview storms and quickly identify high-impact weather events, a novel storm graph visualization to inspect and analyze storm topological changes and structures, as well as a set of interactive features for efficient identification of similar storm sounds. We name analogs. These analog situations are searched in a historical database used for very short-term forecasting. Before entering into the specifics of how our visual design supports forecaster tasks, we will describe the data sourcing use. Hornero currently uses two main data sources. Radar data, coming from the next generation radar, NEXRAD stations, provided by the National Oceanic and Atmospheric Administration of the United States, the NOAA, and structural information of storms detected by TITAN, a thunderstorm identification, tracking, and analysis and nowcasting system of the National Center of the Atmospheric Research of the United States. In TITAN, a storm structure is described as a raster object composed of connected pixels in a weather radar image. TITAN uses minimum and maximum intensity of the reflexivity as a thresholds to identify a storm object and model it as an ellipse. We refer to this as a storm cell. Once the object is defined, it calculates several geometric characteristics like the position of the centroid, its area, and orientation. In our solution, we model a storm cell as a change in a graph structure and save all of their available associated properties as provided by TITAN. We designed our solution with the goals in mind of being expressive, easy to use, and effective to prompt analysis and quick decision making in the context of nowcasting or short-term operational weather forecasting. Each of our decisions was made in a participatory design process together with our domain experts. So I will now walk through those design choices supported by their task workflow. In a surveillance task, forecasters first need to overview the horizontal distribution of the radar reflectivity and then to analyze other derived properties. So to assist them in this task, we designed a map overview showing the latest radar data and the latest detected storm cells. We choose this map visualization because the storms are inherently spatial, and our experts are highly trained in spatial visual analysis. They can quickly identify changes on the map, make rough estimations of distances between 2 points in the map, between 2 storm cells, or time steps, for example, to identify rapidly growing storms, and in this way reducing the cognitive load needed to perform this task. We also provide them with a Focus Plus Context interactive features that allows them to show the contour lines corresponding to this complete storm evolution as contextual information. On top of that, forecasters can add other properties such as volume, cell volume, hail, intensity, and many other properties as new layer on the map. By this means, they can overview at a glance the complete storm development. As a next step, forecasters rank different storm clusters depending on their severity. To help the users to detect relevant information, we provide them with a multivariate visualization tool that shows the different characteristics and allows the users to do a compounding analysis between different variables. For example, here we can see that the user selects and filters properties associated with potential dangerous storms. For example, large cell volume and high intensity. After this step, the user can do further analysis of spatiotemporal features and topological changes on the storm structure. For that, we designed 2 complementary views. First, a trajectory view that shows the different storm branches, reveal turning and splitting and rejoining of the storms, as well as a storm graph structure that is an abstract visualization that can reveal topological changes in the selected storm cells. For example, in this case, the storm cluster presents 3 branches, with bifurcation into the northeast and southeast branch that leads to the development of high-altitude storms that are associated with potential dangerous events. We adapted the graph layout to easily identify storm branches that are geographically close to each other. This is especially helpful when the storm structure is large and contains multiple branches coming from different geographic areas. We added an interactive feature to this graph that provides the options to collapse consecutive time steps into a single glyph, reducing the clutter in the graph displayed. We developed our visual design with a focus on simplicity and aesthetics, provided by the Gestalt laws of proximity by means of geographically clustering layouts, similarity by using similar color encodings, and continuity by adding the interactive collapsible features. After all of this analysis and to complete the task workflow, forecasters now cast and issue short-term warnings about potential severe weather events. Currently, there are 2 groups of operational techniques that can be used and combined to provide forecasters with adequate guidance for issuing short-term warnings. These are numerical prediction and, on the other hand, data-driven prediction systems, also known as nowcasting. Nowcasting uses the latest weather radar data to predict weather events in the range of minutes to a few hours, up to 6 hours. We designed a first visual approach for assisting our experts, operational weather forecasters, in nowcasting. We wanted to enable them to evaluate how likely is that the current storm cell will develop into a dangerous phenomenon, based on the prompt analysis of similar situations in the past we call analogs. So, to support this critical task, we developed a visualization component named the analogs view. We define an analog to a current storm cell, let's say I, as a previous storm cell, let's say J, that is similar to I to a certain threshold. For the similarity measure, we adapted the algorithm provided by Shai al, you can find in our paper, named Saldeda, and defined a weighted function using Titan's output, calculating a weighted difference of volume, difference of area, longitude, eccentricity, and amplitude. Afterwards, we calculated the probability distribution for each available property as it comes from Titans among all analogs and visualize it by means of a histogram, which is a simple visualization that is familiar to our domain experts. We use the same color encoding as the color encoding used for each particular property, and the bin containing the property where the current storm in analysis appear is indicated also in a shaded texture bar. To evaluate our system and design choices, we performed 2 rounds of semi-structured interviews with expert meteorologists at National Weather Services in Argentina, all of them with more than 3 years of experience in operational weather forecasting. And one of them actually is the head of the operational forecasting team at the National Weather Services, and has a strong experience in operational workflow, which was very interesting to us because we wanted to model their workflow. 2 of them also work as operational forecasters, and the other 2 are researchers working at the National Weather Service as well. So the results of our interviews showed that domain experts found the visualizations very to extremely expressive, very easy, and also moderately to very effective. These very positive results were not all. They also proposed the scenarios where our visual tool can work. For example, to perform real-time analysis and post-factum analysis, to monitor the meteorological situation and carry out analysis of the severity potential, and finally to estimate the near future displacement of thunderstorms in between a particular region. After analyzing the very positive results of our interviews cycles, we summarized some lessons learned. For example, our results reinforce the ideas discussed during the application spotlight session in the Visualization in Meteorology and Climate Science session at the VIS 2019, where one of the main claims was that more tailored and user-centered, domain-focused approaches for visualization systems or weather forecasting are needed. On top of that, we also conclude that visual design for quick and high-impact decision-making over large datasets requires user-centered, intuitive, expressive, and low cognitive load, yet effective visualizations. So we will continue working in this area, and a next challenge for us includes working with the additional datasets and formats that can be useful for our domain experts and integrating Hornero into the domain expert current tool set. We are looking forward to do more research together and user studies. With this, we thank you for your attention and we look forward to your questions. Thank you.